Okay, this is the video tutorial that I'm preparing for chapter 3 of my textbook. Uh, the title of the chapter 3 is Elastic Plastic Analysis of a Notched Plate. So let me put this thing in the slide mode so that we can see what we're doing. Here's the book. It's the release 2021x of 3D Experience, how you do finite elements in it with its native FEA solver. And these are the chapters, and we're going to be doing chapter 3. Okay. The problem that we're going to analyze is a very straightforward geometry of a block with a central hole, which is loaded at the two ends. Now, the dimensions of the block are given in a minute, and because of the symmetry, we need to model only 1/8 of this block. Okay, so these are the dimensions, and the applied pressure is 500 megapascal. Young's modulus 200 gigapascal and Poisson ratio 0.3. Now, uh, this is a large load and it's going to put the material, going to push it into the plastic range. So uh, we're going to have to supply this data to the program. What you see here is the yield strength of the material. So 100 megapascal. 100 megapascal is the yield strength, okay? And so this is a true stress versus plastic strain. You're going to have to input this thing in the program. All right, so let me go ahead and log into my account. It's a single part, so we're going to get into the part design. So we go here on the part design. It's going to hook up to the server in Europe, and just bear with me for a second. Okay. The previous chapter, the chapter 2, is the same problem except that it's in the elastic range, and we're going to do that a little bit differently. Okay. The original textbook or the original book was written for release 2017, but it's updated to cover the new icons and some of the new features that are now available. Okay, we're in there. So we are already in part design, as you can see. Uh, let's make our geometry. So we I'm going to double click the 3D part essentials. Okay. So on a convenient plane, on that vertical plane, I'm going to sketch. Uh, basically 1/8 of the cross section. So something like this. Start with this. This is the rectangle. I'm going to draw a circle, and I'm going to use the quick trim to clean it up. There's a quick trim. Get rid of this, get rid of that, and get rid of this. So basically what I have here now is this cross section. Okay, so let's see now. The height is 50 by 75. 50 by 75. Okay, so let's go dimension it. So this is 75 millimeter, and this is 50 millimeter, and the radius, I just noticed that sorry, this is, let me clean this up. This point, this edge control that edge. Why don't I give it a point, make it coincident? Okay, so right there, you make it coincident. Okay, very good. Now 50, 75, that radius is going to be, let's see, what was the radius? The diameter was 25, the radius is 12 and a half. Okay, so the radius is the radius. 12 and a half. Let's say radius 12.5. Okay, I noticed that this line is not coincident with the vertical axis. So I was kind of sloppy when I made the geometry. Okay, so let me make it, what is that, coincident? All right, good. So exit. And we're going to pad it by uh, half of 20 millimeter, which is 10 millimeter. Just notice something. Yeah, pad it by 10 millimeter. 10. So what you see here is basically an eighth of that geometry. Okay, so we can apply material right now. We go to tools. We create our material, create material. Title, I'll call it my chapter 3. My chapter 3 data. And what this thing does is actually it only creates a shell for the material. It creates it and puts it in the database. And if you want to see it, I'm going to sort this out, sort it out according to the date and descending order. So the first one is going to be the one that I just did, my chapter 3 data. And right now I'm going to say right click, apply. I'm going to close this or minimize it, close it, and then apply, put it there. You see that? You put it on this or that, it doesn't matter, or put it on the part and say check. So what it does, it creates a shell. If you expand and double click on it, it opens up, and right now there's no information in there. So we're going to say structural, abacus multiphysics, mechanical. Well, first of all, as far as elasticity goes, we're going to put the Young's modulus, which is 200 e to the 11, 200 e to the 9, sorry, 200 e to the 9. That's your Pascal, okay, and 0.3, okay, or yeah. Okay, so this is the data for elasticity, and then we're going to go to plasticity, metal plasticity, and plastic. Oops. And then what you do is you input that table. You remember that table that I had? You yield the stress versus plastic strain. So first of all, this is isotropic, von Mises yield criteria, and the one way is to write an Excel file and import it, which I'm not going to do. I'm going to just create 7 rows. Right now we have 5. I think we need 2 more. 1, 2, 3, 4, 5, 6, 7. Okay. So let's see now. We put the cursor there, right click. Well, okay, let's type it in. Let's type it in. So the first one was, have to go back and forth between these. 1 e to the 8, 0. 1 point e to the 8 and 0. For the next row is going to be 2.7 e to the 8 and 0.005. 2.87 e to the 8 oops, wrong place, 2.87 e to the 8, 0.005. Let me see for a second, is that what I had? Sorry, 2.7, not 2.87. So this is going to be 2.7, okay? And then 2.69, 2.69 e to the 8, and this is 0.007. This is why it's easier if you wrote an Excel file and imported it, which I'm not doing. And then it's going to be 2.67.01, 2.67 e to the 9, and this is 0.01. Okay, this one is that was 2.67 e to the 8. I have to correct that. This should be e to the 8. 8. The next one is 3.35049, 3.35 e to the, what was it, e to the 3.35 e to the 8, to the 8, 3.35 e to the 8, and 0.049, 0.049. And then we have to create duplicate rows. So let's see now, duplicate row now, and another one. Okay, so let's put second last line here, 4.8.196. So this one is 4.8, 4.8, and what was that? 0.196, 0.196, and finally the last row is 4.88.21, 4.88. I'm sorry, you should have done this thing with an Excel sheet, but and this one is 0.21. Okay, so we should be all right. We don't need anything else. You can always double check that. The data for plasticity is here. You can scroll down. Yeah, and incidentally, what you can do just to check some stuff, you can also plot this data. So you put the cursor there, you can say plot. So it looks like that. Okay. Yeah, this is all right. We're going to finish it. Now, we are done as far as the model is concerned. So let's save everything first. Okay, we then move on to structural model creation. Defaults. Now, in chapter 2, I will do the same problem, except that the concept of abstraction is used there, and I have to pull around with the radio buttons up here. But this, we're not using abstraction here, shape abstraction. Just go ahead and select all the defaults. Okay, now notice that the elements have been created here. The solid section has been created. You can always make changes if you double click on the tetrahedral mesh. You can change the type. Right now it's quadratic. You can change the type to linear. You can make local mesh refinements and things like that. I'm not going to do that. Okay. All right. So that takes care of this, and we're pretty much here. If you want to look at the mesh, by the way, all you have to do is you go there and you say, sorry, you go update. Shows you the mesh. If you want to get rid of the mesh, there are different ways of doing it. One way is to just say model. show me the model, or let's see, right click visualization management, and the mesh don't show it to me, hide it. There. Okay, so this right click visualization management is very useful to do some things on the fly. Okay, so where are we now? We did the mesh right there, and now we're going to go to scenario. So we go to structural scenario creation. As soon as you go there, it asks you whether it's structural or thermal or both. Obviously, our problem is structural, and once you do that, you're ending up with that in that workbench with the action bar shown like that. Notice that there's two red exclamation marks here. You have to get rid of these before you run it. So, for example, when you go to setup, you come across this icon, finite element model. You select it. There's only one here, but it could be that we created several mesh and we want to use a specific one to run it. And I'll do that later in a different chapter. So, but here there's only one finite element mesh that has been created. You select it and you say, okay. Notice that this check mark, this turns into a green check mark. Okay. Now, for procedure, by the way, this is bothering me. So right click mesh visualization for the finite element mesh, don't show it to me, hide it. Okay, good. Now we go to procedure. It's a static problem, static basic static step. Now the only thing is that I suggest that we start with increment of 0.01. Okay, 0.01. The only thing that I change is this 0.01 here, and make sure that the uh, nonlinear geometry is on. I think it's on by default. Okay. Notice that now this one turned green. Now let's go and do the restraints. So for restraints, uh, well, this is a plane of symmetry. You can either use, there's no displacement perpendicular to it. Okay, that's a plane of symmetry. Or you can use the roller support. This is a slider. Okay, you select this and you have to select that. It's a roller basically, and you cannot do this thing. You can select multiple surfaces, but it's going to be wrong. So we say okay. The other slider is down here. So there's a slider. This is down here, and the last one is over there. Plane of symmetry. This thing would have worked also. So there we are. Okay, very good. Nothing else. And then the load. The load is pressure on that face, and positive means pressure. You compress the object, but if this is under tensile load, so this is going to be 50 e to the 6. I think that's what it was, right? The load was 50 megapascal, which is 50 e to the 6. Okay, and nothing else. Oops, I have to put a minus sign here. I don't want to compress it. It's under tension. Okay, so you can see that it's tension. Save everything. All right, I think we have taken care of all the stuff that we want. We go to simulate. First of all, check the model. And simulation check, it went through, no problem. Simulation check. Say okay. That's okay too. There may be some warnings here because of the shape of the elements, or perhaps some distortion, but generally speaking, no issues. Yeah. Okay. And close this, and then we're going to simulate. Now, as this is running, you can show some intermediate results. So for example, you can see the iteration as it's happening. This is a plastic, this is going to plastic range, so there will be iterations, etc. And you can also plot the issue for showing convergence eventually reaching their final load. Okay, and you can also see any messages if you want to see the messages, not the licensing messages here. You see warnings there. You can read these if you want. It's a good idea to read them, but here we are. Uh, so this 500 or 50 megapascal was applied in so many steps, 12 steps, for example. This is the initial step, no 1 mesostress, and then the next one, 1 mesostress is there, and the next one, and you go all the way down to the last one, last step, which the full load of 550 megapascal was applied, and these are the values of 1 mesostress. Now let's check a few other things. So for example, let's look at the displacement. Obviously, the biggest displacement is right there. That's not surprising, and it's 0.02, I don't know, 0.02 millimeter. And you can look at the plasticity, for example, plastic strain. Notice that the plastic strain at the final stage, most of the stuff is over here. At the initial stages, there's no plasticity or very little. Gradually, as you increase the load, in this case, at this stage, uh, and the final stage, there is actually some plasticity taking place. Now, the other thing you can display is what is called uh, active yielding. It shows you what are the places that actually have yielded. So it's in this area. And okay, keep in mind that the nominal stress applied at the end was 50 megapascal. Now we know that from elasticity theory, the stress concentration factor for a plate with a circular hole is roughly 3. So it's not surprising that it yields here because 3 times 50 is going to be 150, and that's past the yield strength. What else do we have here to show you? So you can also show the factor of safety, which shows you basically where is it that it's below 1. Okay, and that's going to be helpful. Now in the book, if you look at the book, there are other things that I've done. I've done post-processing. I've plotted multiple things, uh, so I'm not going to repeat them here. All right, guys, thank you very much. We'll see you in the next tutorial.